Hi Fernanda, this is Dr. Newman. I wanted to create just a short video that will take you through that octet rule. I know that this can be a confusing concept. I have always found it useful to actually write out the electron configuration to kind of see where those valence electrons are, and so I'll take you through a few examples. So before I get into the examples, just a few things to note. So this octet rule is going to only apply to the main group elements. So that's going to be the elements in columns 1 and 2, and then the elements in columns 13 through 18. So these are what are considered the main group elements. Also, when you look at the periodic table, you should realize that the column that elements are in is going to give you a hint about valence electrons. So if you want to go through some of your own examples, you should be able to double check your work. So just as an example, so if you look at the elements in column 1, what you'll find is that these will have one valence electron. Elements in column 2, these are going to have two valence electrons. If we go over here to column 13, these are going to have 3 valence electrons. These will have 4 valence electrons. These elements will have 5. These will have 6. These will have 7, and then the noble gases, this last category, or in this last column, excuse me, are going to have 8 valence electrons. And these are considered to be very stable elements because their outermost electrons are electron orbitals are full. Also, another thing to note, the octet rule is going to apply to the number of electrons in those s and p orbitals. So that's something else to kind of keep track of. Okay, so we'll go through a few examples. Again, there's another thing I just wanted to highlight. So it's important to realize that different orbitals will exist within different energy levels. So I think you had mentioned in your email that you knew that there were different orbitals that exist. So there's the s orbital, which can hold 2 electrons, the p orbital, which can hold 6, the d orbital that can hold 10, and then the f orbital that can hold 14. These orbitals are going to fill up with electrons in a specific way, so it's not strictly going to be by energy level. They're gonna fill in a way similar to that image that I had shown you, where you'll have 1s filling first, and then you'll have 2s filling, and then you'll have 3p, and then 3s, and then 3p, and then 4s. As you get into elements that have more electrons, things start filling in ways that maybe you didn't predict. So for example, here we have 3p fills, and then 4s fills, and then that d orbital 3d starts to fill, and then 4p. So things aren't strictly filling by level 3, level 4. The orbitals fill in a slightly different way, and so this is something that you kind of need to keep track of when you start looking at the electron configurations for certain elements. So we're going to look at a couple different elements again, just so you can get an idea of how electrons are filling these orbitals, and again, where those valence numbers are actually coming from. And so I'm going to start here with sodium. So sodium has 11 protons, that's its atomic number, and so if it has 11 protons, we know it also has 11 electrons. And sodium is in column 1, so we would predict that it would have 1 valence electron. So if we go through and look at the electron configuration, again, there's 11 electrons, and if we follow this diagram of how things are going to fill, we see that the 1s will fill first, the 2s will fill, the 2p will fill, and then our 3s orbital will get 1 electron. So again, if you go through and count, this is 2, 4, 10, and then there's our 11 electrons. So we have in this outermost electron shell, so this third shell, or energy level, there is 1 electron. And again, that's what we predicted when we looked at this column number. So we predicted that there would be 1 electron in that outermost shell, in that valence shell. So now we can look at something that has slightly more electrons. So in this case, we'll look at something like calcium. Calcium, again, it has an atomic number of 20, so that means it has 20 protons, so it also has 20 electrons. We see that it's in column 2, so we would predict that it would have 2 valence electrons. Okay, so looking at calcium, again, 20 electrons, so 1s is going to fill, 2s will fill, 2p fills, 3s fills, 3p fills, and then that 4s, that 4s orbital gets the remaining 2 electrons. So again, if you go through and count 2, 4, this would be 10, 12, 18, and then there's our 20 electrons. So in this fourth energy level, so this 4s shell, we have 2 electrons. So again, those are what we would consider to be our valence electrons. Now let me go back here to sodium. So sodium has this 1 electron in its valence shell. Remember, with the octet rule, things are trying to really fill up their outermost electron shells. And again, this is pertaining to those S and P shells. It really wants to have that 8, okay, because between the S and the P, you could have a total of 8. In this case, it only has 1. And so there's a few different options that sodium has. Sodium, again, it's sitting in column 1. One of the things you would find as you continue to study chemistry and biology is that things that are in column 1 tend to give up that 1 electron. When they give up this 1 electron, they're essentially left with their valence shell, this second shell then, that is full with 8 electrons. And so these tend to be elements that will give up electrons. So some elements will pull electrons toward them and some will give them up. Sodium tends to be one that gives it up. Calcium is a similar situation. It's easier to give up those 2 electrons than it would be to gain 6 electrons to fulfill that octet rule. So let's look at one more, and specifically we'll look at lead. So Pb is the symbol for lead, and this will give you an idea of how some of those d and f orbitals are filling as well. So lead has an atomic number of 82. So this means it has 82 protons, and so it also has 82 electrons. Okay, so in this case, we are going to need to kind of expand out a lot of these orbitals. So we have 1s2, 2s2, 2p6, 3s2, 3p6, and we fill up our 4s2, then 3d fills. So here we go from 4s to 3d, so this is 3d10, then we go to 4p6 and 5s2, then we have 4d10, 5p6, 6s2. So again, this gives you an idea that things aren't necessarily filling according to energy level. It's slightly different. So 6s2, and then from here you go all the way up to 4f14, 5d10, and then 6p2. So if we go back and look quickly at lead, we see that here's 1, 2, 3, 4. We would expect it to have 4 valence electrons. And again, if we look at the S and P orbitals, and in this case, this 6 energy level is kind of our outermost level. Between the S here, the 6S, and the 6p, we have 2 and then another 2, so that's 4 electrons. So those are our 4 valence electrons. And again, lead is going to participate in chemical bonding to try and fill up its outermost S and P orbitals to fulfill that octet rule to get those 8 electrons. So hopefully that gives you a little bit more of an idea of how things are filling. I think, in most courses, especially, general biology courses, textbooks tend to focus on, things in these first 2 columns, the really easy things to kind of get an idea of where electrons are. Things can get slightly more complicated as atoms get bigger. But this is something that you can practice on your own. Maybe you want to go through something like bromine, and practice drawing the electron configuration and seeing if you get 7-valence electrons. So again, hopefully that gives you a little bit more of an idea of what's happening. Please let me know if you have any more questions.